In the summer of 2025, in a quiet corner of an astronomy conference, a French astrophysicist named Anne-Marie Lagrange looked at a faint orange smudge of infrared light sitting inside a swirling ring of dust and debris, and realized she was looking at something that had never technically happened before in the entire history of the James Webb Space Telescope. Not a confirmation of a planet already known to exist, not a spectrum analyzing a world discovered years earlier by some other method. An actual, brand new planet, never previously detected by any instrument, found for the first time simply because Webb managed to see it directly, sitting there in the dark, 111 light years from Earth. When the discovery was published that June in the journal Nature, the language used by the researchers involved was almost unusually direct for a scientific paper. This was, they confirmed, the first time the most powerful space telescope ever built had discovered a new world purely by photographing it, not by watching a star flicker as something passed in front of it, not by measuring a star's wobble as gravity tugged on it from some invisible companion, by actually capturing its light. Stay with me, because this is the story of how that image happened, why doing it at all pushes right up against the technical limits of modern astronomy, and why the planet Webb found is unlike almost anything discovered before it. To understand why this moment mattered so profoundly to the researchers who found it, you first need to understand just how rare direct imaging actually is in the entire field of exoplanet science. Since the first exoplanet orbiting a sun-like star was confirmed back in 1995, astronomers have identified more than 5,000 planets orbiting other stars, and the overwhelming majority of them were never actually seen. They were detected indirectly, through methods that infer a planet's existence without ever capturing its own light. The most common method, called the transit method, watches a distant star's brightness for the tiny, repeating dip caused when a planet passes directly in front of it from our point of view, a shadow so faint it might dim a star's light by a fraction of a percent for just a few hours. Another common method, the radial velocity technique, measures the subtle gravitational wobble a planet's orbit induces in its host star, detected as a rhythmic shift in the star's light spectrum. Both methods are powerful, and both have found thousands of worlds, but both share the same fundamental limitation. Neither one actually shows you the planet. You're reading a shadow or a wobble, and inferring a planet must be there to cause it. Direct imaging, actually capturing a planet's own light in a photograph, is almost absurdly difficult by comparison, for one simple, brutal reason. Stars are blindingly bright, and planets, even large ones, are staggeringly faint next to them. A star like our own sun outshines a planet like Jupiter by roughly 1 billion times in visible light. Trying to photograph a planet next to its host star is often compared, by astronomers themselves, to trying to photograph a firefly hovering directly next to a lighthouse beam from thousands of miles away, and picking out its faint glow without being completely overwhelmed by the light source sitting right beside it. Before Webb, only a small handful of exoplanets had ever been directly imaged at all, and every single one of them was a very young, very hot, very large gas giant, planets still glowing with residual heat from their own formation, orbiting far enough from their host star that there was at least some meaningful separation between the blinding light source and the faint object astronomers were actually trying to see. Webb's own first direct image of an exoplanet came in September of 2022, when astronomers led by Sasha Hinckley at the University of Exeter captured images of a gas giant called HIP 65426b, sitting roughly 100 times farther from its star than Earth sits from our sun, a distance generous enough to let Webb's coronagraphs, specialized instruments designed to physically block out a star's overwhelming glare, isolate the planet's own faint infrared light cleanly. Hinckley described the achievement in blunt, genuine terms at the time, calling it a transformative moment not just for Webb, but for astronomy generally. That image was a landmark, the first proof that Webb's instruments were capable of this kind of observation at all. But HIP 65426b was not a new discovery in the truest sense. It had already been identified years earlier using other observatories. Webb was confirming and imaging something astronomers already knew was there. TWWA7B, the planet Lagrange's team announced in 2025, was different, and this is the distinction that makes it genuinely historic rather than simply another impressive photograph. Nobody knew this planet existed before Webb found it. It had never been detected by any transit survey, never picked up by any radial velocity measurement, never suspected by any prior observation of any kind. Webb found it purely by looking, the single hardest and rarest way any exoplanet has ever been discovered. The star at the center of this story, TWA7, sits roughly 111 light years from Earth and is remarkably young by stellar standards, only around 6 million years old, a newborn compared to our own sun's 4.5 billion years. Young stars like this are frequently surrounded by enormous flattened disks of leftover gas, dust, and debris, the raw material left over from the star's own formation. material that, given enough time, can clump together under gravity to form planets. TWA7's debris disk was already well studied before Webb's observations, known to contain 3 distinct concentric rings of material, structured almost like the rings of Saturn stretched out across an entire star system. What immediately caught researchers' attention was a conspicuous, empty gap carved into one of those rings, a clean, well-defined break in the disk's structure that planetary formation theory strongly suggested could be caused by a planet's gravity actively clearing debris out of its own orbital path as it moved. Using Webb's mid-infrared instrument, known as MIRI, along with a coronagraph specifically engineered to suppress the otherwise overwhelming glare of TWA7 itself, Lagrange's team pointed the telescope directly at that gap and captured a faint but genuine source of infrared light sitting precisely where theory predicted a planet ought to be. The signal was compact, distinct from the surrounding disk material, and positioned exactly inside the cleared gap the researchers had already identified as a likely planetary signature. Careful analysis of the light's properties strongly suggested it was not simply a background object coincidentally aligned with the disk. Researchers calculated the odds that this faint infrared source was actually an unrelated background galaxy happening to sit in exactly the right spot, by pure chance, at only about 0.34%. A small enough possibility that the team felt confident describing the object as a genuine planet rather than a statistical fluke. What they found was almost as remarkable as the discovery method itself. TWA7B carries a mass roughly comparable to Saturn, making it, at the time of its announcement, the lightest exoplanet ever successfully captured through direct imaging, a genuinely significant technical milestone in its own right. Every previous direct image of an exoplanet had involved considerably larger, more massive worlds, simply because bigger, heavier young planets tend to glow brighter, with leftover formation heat, making them comparatively easier targets even with the extraordinary difficulty direct imaging already involves. Finding something as comparatively small and faint as a Saturn-mass planet, glowing at an estimated temperature of only around 120 degrees Fahrenheit, considerably cooler than most previously imaged exoplanets, pushed the boundary of what direct imaging technology could actually achieve into genuinely new territory. TWA7B orbits its star at a distance of roughly 5 times the separation between Neptune and our own Sun, sitting far out in its system's icy outer reaches. Embedded directly within the gap, it appears to have carved into its parent star's debris disk. Why does finding a planet this small and this faint actually matter, beyond simply setting a new technical record? Because the entire long-term ambition driving direct imaging research is not, ultimately, about photographing enormous, blazing hot gas giants. It is about working steadily toward the extraordinarily difficult goal of eventually photographing something considerably smaller, considerably cooler, and considerably harder to detect. A rocky, potentially Earth-like planet orbiting at a comfortable distance from a sun-like star, cool enough to potentially host liquid water on its surface. Every previous direct image milestone and every new record for the smallest, faintest planet ever successfully imaged represents another incremental step down that same difficult technical path, refining coronagraph performance, refining image processing techniques, refining the entire chain of engineering required to suppress a star's blinding light well enough to eventually spot something as comparatively dim and small as another Earth. TWA7B, at Saturn's mass, sits nowhere close to Earth's scale yet, but researchers studying the discovery have been explicit. That finding a planet this comparatively light and cool represents genuine, measurable progress toward instruments someday capable of managing exactly that harder task. This discovery also arrived alongside a broader wave of direct imaging results Webb has produced across the past 2 years, each pushing the technology in a slightly different direction. In July of 2024, astronomers used Webb to directly image a cold super-Jupiter orbiting a star in the nearby triple star system Epsilon Indi, a discovery notable for how much colder and older the planet turned out to be compared to most previously imaged worlds, opening what researchers described at the time as a genuinely new window into studying planets more similar in temperature and age to the mature gas giants found in our own solar system. Rather than only the young, blazing hot planets direct imaging had mostly been limited to detecting before. In June of 2025, in a separate study, Webb captured strikingly detailed images of 2 giant exoplanets orbiting a distant sun-like star, revealing sand like silicate clouds and evidence of active moon-forming material swirling around them. The kind of fine atmospheric detail direct imaging had never previously been sensitive enough to resolve. And earlier this year, in a related but distinct milestone, Webb managed to directly study the actual surface, rather than the atmosphere, of a rocky exoplanet called LHS 3844b for the first time, a so-called super-Earth, roughly 30% larger than our own planet, sitting nearly 50 light-years away, revealing what researchers described plainly as a dark, hot, barren rock, an achievement that pushed exoplanet science into analyzing solid planetary surfaces directly, rather than only atmospheric compositions, a technique researchers explicitly described as the next necessary step toward eventually understanding the true nature of small, rocky worlds beyond our own solar system. Taken together, these results paint an honest, unhurried picture of where exoplanet direct imaging genuinely stands right now in the middle of 2026, considerably more accurate than any single headline claiming a single dramatic breakthrough. We are not yet capable of photographing another Earth, and no credible researcher working in this field is claiming otherwise. What has genuinely happened is a steady, carefully documented sequence of improving capability. Smaller planets, cooler planets, planets discovered for the first time purely through direct imaging rather than confirmed after being found some other way. Each new result nudging the achievable boundary of this extraordinarily difficult technique a little further than it stood before. TWWA7B's discovery specifically matters because it demonstrates for the first time that Webb is capable of finding entirely new worlds this way, not simply photographing planets. Other instruments had already flagged, a distinction that separates a genuine discovery from an impressive confirmation. Lagrange and her research team have been clear that TWWA7B's identification, while strongly supported by the available evidence, still awaits additional confirming observations before the astronomical community considers it fully, permanently settled, precisely the kind of careful, appropriately cautious language that separates responsible science from premature certainty. That caution does not diminish what was actually achieved. It reflects exactly how real scientific discovery is supposed to work, methodical, transparent about remaining uncertainty, and willing to state plainly what still needs to be verified, rather than declaring victory prematurely. What is not in question is the underlying technical achievement itself. An infrared telescope originally built primarily to study the earliest galaxies in the history of the universe turned instead toward a nearby 6-million-year-old star, managing to suppress that star's overwhelming glare precisely enough to capture the faint, genuine light of a Saturn mass world that no human being had ever seen before the image was taken. Somewhere out there, roughly 111 light-years from where you are right now, a young planet is still carving its own gap through a ring of dust and debris left over from its star's formation. Exactly the kind of process that once shaped our own solar system billions of years ago. We can now actually see it happening, not infer it, not calculate it from a shadow or a wobble, but see it directly in an image captured by an instrument that keeps proving it was built for more than anyone originally imagined. If you want to see the next new world, Webb manages to photograph directly, and how much closer each discovery brings us to finally capturing an image of a true Earth twin somewhere out there. Subscribe and turn on notifications, because this technology is still improving fast, and the next headline might be closer to home than anyone expects.